Joining us today is Dr. Dominic Benford, the program scientist for the Nancy Grace Roman Space Telescope. Dr. Benford, welcome to Cool Science Radio.
Thank you, Scott. I'm excited to be here. I've got a great telescope to share with you today.
Yeah, so let's first things first. Who was Nancy Grace Roman and why is this telescope named for her?
Nancy Grace Roman was hired in 1959 to be NASA's first chief of astronomy. And in that role, her job was to make space telescopes possible. When the agency started, this had never been done before. And she became the person who led all of the first astronomical observatories in space. The final project that she had started before her retirement was then called Space Telescope, and we now refer to it as the Hubble. And she's often called the mother of Hubble. And we've decided to honor her and her legacy of space telescopes by naming the Nancy Grace Roman Space Telescope for her.
And what's different about this space telescope than, say, the Hubble or the James Webb?
So the Roman Space Telescope is a survey machine. We designed it to image the universe far faster than has been possible with either Hubble or Webb. The things that make it really predominantly different are the fact that it has a telescope that's the same size as Hubble, and so it gives you the same sharpness of image and the same light gathering power, but it has a camera and a field of view that is over 100 times larger. So it can image the universe with much, much larger photos. And it is a much more agile observatory, so it can take pictures far faster. Those together mean that Roman can image the universe 1,000 times more rapidly than Hubble can. Hubble's been going for more than 30 years, has returned phenomenal images of the cosmos, but has only observed about 1/10 of 1% of the sky. Roman intends to change that drastically by being able to image more than 10% of the sky in just the first 5 years.
Well, that's remarkable. Now, I understand that this telescope is, you said it's about the same size as Hubble, so the size of, I guess, of a semi truck, if I remember this correctly. But it has the cameras the size of a refrigerator. Can you tell me a little bit more about the cutting edge technology that's behind those cameras and the technology this telescope is carrying?
The Roman Space Telescope has an enormous camera, which has been put together with a 300 million pixel focal plane array or detector array that gathers the light. Compare that to the 1 million pixel detector that's in the Hubble Space Telescope's infrared camera right now. And you can see that the march of technology over the last almost 2 decades has given us the possibility to image the universe with far more uh, detectors, far more pixels than has ever been possible before. Now, when you have that capability, instead of looking at an individual galaxy or a star or a small number of galaxies or stars, like is done with Hubble and Webb, Roman, with every single deep image, will find a million galaxies. And over the course of many, many images, we'll find billions of galaxies. And looking into our own galaxy, we'll see billions of stars. And when you have that kind of capability, you can use it to address new science investigations that have never been possible with something like Hubble or Webb because they simply would take too long.
So, again, this is going to be a lot of data to be processed. How is that going to happen?
The Roman Space Telescope will generate data and send it to Earth across a million miles of space at a rate of about 1.4 terabytes per day. And if you compare that to the Hubble Space Telescope, which has been operating for more than 30 years and has sent down a total of about 200 terabytes, Roman, in its first 5 years, will have an archive of more than 20,000 terabytes. All that data will exist on the cloud with no period of limited access so that anybody, anywhere can get access to that data and start looking at it and making scientific discoveries with it right away. It's all in the cloud so that everybody has equal access to it.
Everybody?
Anybody.
Wow. I'm going to have to get the address of that
Well,
website.
first,
Now,
go to nasa.gov/Roman, and that's where we will have updates. And from there, you can find how to get access to the data. Now, of course, we haven't started observing yet, but we will when it launches this September.
do we have a firm launch date yet?
So we are ready to launch by the early September of this year,
And
weather permitting.
how will people be able to follow along with that launch? Will there be a website where we can watch the physical launch?
So we will have access to that at nasa.gov/Roman. You can also look for us on our social media, either at NASA or at NASA Roman on the usual platforms.
So I want to go back to Hubble for just a second because it famously had manned maintenance missions where we were able to actually send people into orbit uh, to hook up with the Hubble and do some repairs and extend its life. Has there been any lessons learned from the Hubble for the Roman telescope? In other words, will the Roman be relatively self-sufficient, or are we going to rely on maybe some human accessibility, human intervention to for repairs?
The Roman Space Telescope was designed to carry into space everything that it needs for a successful and, in fact, transformative science mission over the course of many years. That means that it has a camera that is at the state of the art and is unlikely to be superseded by technology anytime soon. So we did not envision a need to replace it with anything, as opposed to the Hubble Space Telescope, where it was always envisioned to have replaceable instruments. The only consumable on the Roman Space Telescope is fuel, and that's what will ultimately limit its usable life. And the Roman telescope is refuelable on orbit, should that capability exist. And so it's possible that we could extend its life by adding fuel to its tanks.
That's amazing. So we are expecting it to run again. Can you tell me again how long we expect the Roman telescope to be working just on its own? Was it 5 years?
It, the Roman science mission, as currently planned, fits within the first 5 years of observing, but we designed the observatory to last at least 10 years. And so it should have enough fuel for that and perhaps beyond if we use the fuel judiciously.
Well, speaking of design, I'm really curious because, of course, we all watched with bated breath as the James Webb Telescope deployed all of these very complicated mirrors on pulleys and systems. And wow, I can't even remember how many moving parts there were on the James Webb, but I remember it being an incredible engineering feat. And then to watch all of these mirrors unfold, it's almost like a ballet in space. Now, I understand that four of the six solar panel sections have to fold against the Roman spacecraft to actually fit inside the Falcon Heavy rocket that's lifting it to orbit, and then swing out in space from one large flat plane. Now, how does that maybe compare? And I guess it's sort of like origami style if I'm, thinking about this. But how does that compare to other design decisions that you learned from the James Webb?
The James Webb Space Telescope is certainly one of the most advanced and complex uh, deployable structures ever put into space. Not only did the telescope's primary mirror have to move into its precise configuration, but the secondary mirror had to be deployed, and a vast sun shield about the size of a tennis court had to be unfolded in a, as you said, origami-like fashion, uh, very slowly and carefully over the course of time. Now, the Roman Space Telescope has some deployments on it, but they were all designed to be much simpler and more robust. The solar panels that fold out are relatively rigid and are on hinges, and so just open the way any hinged door would open. The deployable aperture cover that covers the entrance of the telescope and protects it during launch unfolds a little bit like an umbrella. And the high gain antenna that we use to send all that data back by radio, is a relatively straightforward gimbal mounted uh, item that has motors that drive it. So, again, these are things that we know how to do. And so we're very confident that it will deploy smoothly shortly after launch.
So I guess that begs the question, how did this program end up 8 months ahead of schedule? And I hate to continue to compare it to James Webb, which I know took a little bit longer. I want to say it was maybe 7, 8, 10 years past what we thought the project date was. But man, how did you get the Roman telescope so far ahead of schedule?
I was holding that cough for a moment. Edit that part out.
No worries. That's why we edit.
The Roman Space Telescope was predicated on a set of advanced technologies that we knew how to do when we started the mission, and we knew what to invest in. And we designed the mission to be built by a number of expert teams across the country and brought together at NASA's Goddard Space Flight Center, with NASA essentially acting as a prime, putting everything together, doing all the integration and the testing to make sure that the observatory worked correctly. Having control over doing that in-house allowed our expert team to focus on how to do things properly, but also promptly. And they managed to do this by reassessing the schedule sometimes more than once a day to rearrange the order in which things were being done, to take account of any hiccups, so that we were able not to lose any time during integration and testing. And that's really what slows down observatories, when you come across an anomaly and you take time to assess it and everything stalls out. We didn't do that with Roman because we had parallel paths and were able to rearrange and focus on things that could be focused on, and therefore actually accelerate the schedule so that things continued over the course of the last many years to get earlier and earlier.
Well, speaking of things to focus on, I know that is the buzz around the Roman telescope is about looking at dark energy, dark matter, exoplanets. If you could just take a moment and tell our listeners what is dark energy, dark matter, and what in the world is an exoplanet and why do we care? Now, I say take a moment. I'm hoping you'll take a lot longer because I think it's a really interesting thing that we're going to be looking for with this telescope.
Thank you for the question, Scott, because Roman was built not only for an amazing capability, but to address some of the most important fundamental questions that are still outstanding in our universe. One of those is about the the twin aspects of our universe that we call dark matter and dark energy. Now, together, they make up more than 95% of the total of matter and energy in our universe. And we refer to them as dark because there is no way to see them. They don't interact with light. There's no way for us to detect them in a laboratory that we know of. But we can see how those twin components have caused the universe to evolve over cosmic time and have made the universe the way we see it today. The stars, the galaxies, the planets that have formed have all done so by being driven by the gravity of dark matter pulling things together to form galaxies, to form stars, to form planets, and dark energy, which pushes the universe apart and has in fact been accelerating the expansion of the universe for the last several billion years. Now, these aspects of the universe we know well because we have detected them using a combination of previously existing observatories, and we can see the effect that they have on the universe. But we haven't been able to gather enough data to study their effects in enough detail to understand why they are the way they are. Why is dark matter distributed the way it is through the universe, and how does it cause galaxies and clusters of galaxies to form in the early universe? Why is dark energy only relatively recently the dominant force in our universe? For the last half, roughly, of the history of the universe, it has been the thing that dominates. Whereas there was no particular reason why it had to take over and become the most important thing. So we would like to understand this, and to do so, you have to measure the way the universe behaved over cosmic time. We have to look at the distribution of hundreds of millions of galaxies from the edge of the observable universe at the furthest possible eras, the most distant in time as well as in space, all the way to the present day, and understand how the universe has evolved. And that'll tell us what we need to know in order to understand what dark matter and dark energy are and how they're going to influence the rest of the universe and what the ultimate fate of the universe may be. So that's the first question, Scott. You also asked about other worlds, worlds around other planets. We call exoplanets the name for a planet that's around another star. We already know of about 6,000 exoplanets around other stars that have been detected by various methods. But because of the techniques we've used, we tend to find only very large planets very close to their stars. So think about a planet the size of Jupiter, but closer to its star than Mercury is to our sun. Now, that's an unusual sounding thing because obviously we don't have a planet like that in our solar system. And in fact, if we had taken NASA's Kepler Observatory or NASA's TESS Observatory, which are the two uh, best planet finders we've been able to bring to bear thus far, if we turned those telescopes to look at our own solar system or a system like ours around another star, we would see none of the planets in our solar system because they haven't been at the right locations. They haven't been big enough and close enough. When we do the same thought experiment for Roman, looking at a solar system like ours, we would see every planet in our solar system except for Mercury because it's a little bit too small and too close. But in exchange for that, we would be able to see things like the giant moons of outer planets like Ganymedes in other solar systems. And once we can do that, we can answer the question of whether solar systems like our own might be common or rare or perhaps even unique in our universe. And that really gets to a fundamental question that people have asked for as long as there has been history. The question is, are we alone? Well, the first part of answering that is to know whether a planet like ours, a rocky planet that's close enough to its star to have liquid water on its surface, is a common feature of planetary systems or a rare feature. We don't know of very many, if any at all, but it might be that planets like ours are in fact common. And that will help eventually get to answering the question of whether life exists on other planets. That's not something we're going to do with the Roman Space Telescope, but we are carrying a technology demonstration instrument called a coronagraph on Roman. What a coronagraph does is, with very complex active optics, manages to suppress the light of a star so that you can see the reflected light of a planet orbiting that star, which from our vantage point is extraordinarily faint and extraordinarily close. It's like looking for a firefly next to a searchlight, except that you're in this case, Utah, and the searchlight is in New York City. And you have to look at it from such a distance and see that tiny little firefly next to that searchlight. So, but if you can block the light of the searchlight well enough, you can see the firefly. Roman will carry an instrument that is designed to do that, blocking the light of a star to a few parts per billion. And that will allow us to see the planets like Jupiter and Saturn orbiting another star, and we can look at the atmospheres and get some sense of their colors. And in a future observatory, which we've already named the Habitable Worlds Observatory, which will build on the technologies that we're demonstrating with Roman, but with a larger telescope that can block to perhaps a few parts per billion, we would be able to measure the atmospheric chemistry in the reflected light of planets around other stars and look for the chemical elements such as oxygen, carbon dioxide, methane, and ozone, which taken together are indicative of life on the Earth. And if we saw them on another planet, would be potentially indicative of life there as well.
So another analogy, I guess, would be if I'm looking up at the sun, trying to maybe see something in the sky, say a plane is flying by, and I hold up my hand to sort of block the sun a little bit to shade my eyes so I can actually see that plane. Is that kind of akin to what we're talking about when we're talking about dimming, I guess, the output of these stars so that we can see the planets that are closer that we normally wouldn't see?
Yes, Scott, that is exactly right. Uh, in fact, the name coronagraph comes from instruments that were used to observe the corona of our sun, which normally can only be seen during total eclipses when the moon does the job for us. It blocks the sunlight. But yes, almost everybody has experienced this themselves. Typically, if you're playing outfield in baseball, you will note that the sun is always somehow in your eyes, and you always have to put your hand up in order to block the sun so that you can see the ball that might be hurtling towards you at 90 miles an hour. Now, in this case, we're not looking for something that's moving so fast, but we're looking for something that is extraordinarily small and faint and very close to the star. And that's what makes this so difficult and why we have to have such advanced technology to do the job for us. So rather than having a large black disk going over the front of the star, which is the way we would do this for our sun, we need to have a precision set of what are called deformable mirrors that we use to adjust the the performance of the telescope to make it even more perfect than it would ordinarily be and compensate for any aberrations. And then a system of what we call masks, which are they're a little bit like doing magic with physics. They carefully control the diffraction of light through the telescope in ways that manage to suppress the light from the star, but don't suppress the light from the planet. And to do that to the level of parts per billion is truly almost magical.
It sounds like a magic trick.
Our technology has moved forward quite a lot so that we can do this kind of thing by carefully controlling the way light behaves. We understand the physics of it, and it's just been a question of manufacturing these precision optical surfaces.
So back to exoplanets for a moment. Are we looking for, we know exoplanets exist. We've seen them. We know that they orbit other stars. But are we looking specifically for exoplanets that have some type of atmosphere? I think you had mentioned just a few moments ago that the technology is evolving or maybe even exists where we can see refractions of atmospheres. Is that what we're going to be looking for with this current technology or the technology to come?
The Roman Space Telescope's coronagraph is designed to be able to block the light of a star so that we can see the reflected light of the planets around that star. Now, when you're looking at a planet in our own solar system, we're seeing reflected light from the sun, and we can understand something about the way planets' atmospheres work by looking at that reflected light. You can see that Jupiter has bands of clouds, that Venus has a very thick cloud layer, that Mars has a very, very thin atmosphere. You can see all the way to the surface on Mars. And of course, on our moon, you can see the surface of the moon perfectly because there's essentially no atmosphere. So you're seeing all of that by looking at the reflected sunlight, not the planet's glow itself, but by reflected sunlight and using that to understand what the atmosphere is like. We will be able to do the same kind of thing with the Roman Space Telescope. And in this case, we can't take pictures that will resolve the bands of clouds like you can see on, for instance, Jupiter, but we can see the overall colors of those clouds. And that tells us something about what the atmosphere is like.
So we have the Roman is about to launch. We have the Hubble. We have the James Webb. We also now have the Vera C. Rubin Observatory here on Earth, I believe in Chile. How do these three or four different types of technology work together to help us understand our universe?
We designed the Roman Space Telescope to work synergistically with other observatories. For the observatories in space, Roman serves as the method for discovering the most interesting objects to study, the most interesting stars, the most interesting galaxies, perhaps the most distant galaxies in our universe, which we can then follow up and study in detail using tools like the Hubble and Webb space telescopes, which were designed with a suite of tools that allows them to learn about the underlying physics of how objects in space work. But they are designed to look at only a small number of objects, individual stars or individual galaxies. But you have to use a tool like Roman to pick out the very best ones that teach you the most about how the universe works. Now, we also designed Roman to work synergistically with observatories on the ground. Roman is a wide field infrared survey telescope that operates typically in the wavelengths just a little bit beyond the visible and which are easily observed from space and not so easily observed from the ground. The Vera Rubin Observatory that operates on the ground will also have a wide field camera, but operate at visible light wavelengths. And so the two of those together provide a more complete picture of the vast panoply of stars and galaxies in the night sky. And so together they will actually produce much more information about stars and galaxies than either one of them would on its own. And we designed it that way on purpose. And in a way, it's a very fitting tribute because Vera Rubin and Nancy Roman were both astronomers who worked in the Washington, D.C. area and, in fact, knew each other and worked together.
Before I let you go, what is the one major thing you would like our listeners to take away from this conversation about this exciting technology and the impending launch coming up in September?
Well, Scott, I'll tell you what I'm excited about, that we are about to deliver a new capability that will be revolutionary in astrophysics. because we'll be taking data so much faster than has been possible in the past. And with it, we know that we will answer these fundamental questions about dark energy, dark matter, and exoplanets. But what's truly exciting is that the vast amount of data that we generate will be made publicly available as soon as it is processed for everybody around the world to make the discoveries that you can make when you have thousands of terabytes of new imagery. And so the most interesting discoveries that Roman makes will probably be the ones that we can't even speculate about at the moment, because there will be aspects of the universe that we don't understand and don't know about, essentially questions we don't know to ask. It's been said that the most interesting phrase in science isn't aha, but rather, that's odd. So we're going to look for all the unusual things that we can't understand. And Roman, plus the combination of the thousands of people who will use Roman data to make discoveries, will be transformative in our understanding of our place in the universe.
So essentially, we're looking for answers we don't even know the questions to ask yet.
We built Roman to have such sweeping capabilities that it will remain a valuable facility for decades to come.
Dr. Dominic Benford, the program scientist for the Nancy Grace Roman Space Telescope, has been our guest today on Cool Science Radio, and it has been cool science indeed. Dr. Benford, thank you so much for being our guest today on Cool Science Radio. I really appreciate your time.
Thank you for having me, Scott. It's been a pleasure.